done again. So we talk about, so for Gaussian, that if you remember, we have a multivariate Gaussian, like with, let's say, C with some mean, like mu C and covariance matrix C. So what we get is, like, let's say if our C can be written as a two segments, so this both of them are vectors. Like, of course, this is vector as well. So if we observe like part of it, let's say we observe y, like as some small y there, then basically the new distribution is still like Gaussian. I mean, the remaining x, like after the observation of this y here, is still Gaussian, and the mean will become like mu x, the original mean, but it will be like modified by kind of adjust by like the difference between like observed y from the mean y, and you can think of like, I'm going to normalize that. So because this is the variance, right, basically you have the inverse variance, covariance is kind of normalize that, and then I transform from y to x, then you are in the kind of the x domain, you can think of. Then this is like the adjustment of your new mean there, and the covariance will become sigma xx minus sigma xy, sigma y inverse, and sigma
So that is change.
yx.
That is change coordinate.
You can think of that way, right? Because you have this is a okay. For example, this is 5 dimensions here. Like you have 3 dimensions from y, 2 dimensions from x, right? So you are kind of like after this part, like you have like something like it's like still 3 dimensions, right? Then you have from y shift to like this letter 3 s's here, 3 components here to the first 2 components, and I don't know whether like I should say like change of but it's like transform from the y space to the x space, right?
Change size.
Yeah. That in general you will have change of size. So from the size from like the size of y to the size of x there, and that's the observation, right? And I'm actually I mentioned like, actually before showing you that.
Before is variance. That is covariance.
This is covariance also. Like
Yeah,
this is a all this is covariance. This sigma c, or like I should say just sigma maybe.
But why it should be plus mu x?
This is original mean of x.
So that we want to see covariance, or we want to see a mean? Why it should be plus?
So this is the new mean, right? This is the new mean. This is the new mean.
That is new.
So new mean of x. After observing y as small y,
Yeah.
then you have a new mean of x is like mu x. But there's some adjustment there. The adjustment will according to like your observation. If your observation is is exactly equal to mu y, then there will be no adjustment. But if like it's like different from mu y, then you have a kind of adjustment like that. Yeah. And this I'm actually from this we can show a lemma is basically like before that, let me define something called like rho xy. This is just a number. Let's say xy now is just a scalar random variables. So this is the correlation coefficient. Rho xy is the correlation coefficient. So the correlation coefficient is equal to the basically the variance wait. This is not right actually. Let me just write as expectation. x minus mu x, y minus mu y, x minus mu x square right. So, and of course, like this above is just a sigma xy, right? And this is a sigma xy over sigma xx square square root of sigma where's that? Yeah, sigma xx square root and sigma.
Normalization.
Yes, that's basically normalizing the covariant correlation or covariance, yeah, covariance and coefficient between x and y. So here is just scalar. So but you can see that because this normalization, basically this value is basically between 1 and minus 1. It will be like bounded by 1 and minus 1. And yeah, you can whether I need to show that, like I don't know whether I was not prepared to show that, but I think you can quite easily show that, like this is just this is actually just the Cauchy-Schwarz inequality, I believe. So you have, yeah, but let me just let me don't jump into that because I was not prepared. Probably I was stuck. So
But then this 0, it means that we don't have correlation.
yes, in the same when yeah, exactly, when it's 0, then there's like correlation, like it's not correlated, like it'll be uncorrelated essentially. And so with this correlation coefficient, actually, we can show that, like if like now if we assume that x, y, z now are Gaussian, like joint Gaussian, then we will have like x and y is conditional independent to each other given z, if and only if rho x z rho y z is equal to rho x y. So this is pretty easy to show because if we yeah, we're going to prove that. Yeah. So because from what basically we just used our results earlier. So if I write x, y, z as one vector like that is here, like without loss of generality, let me assume to be zero mean. It'll be easier. So assume it's to be zero mean. If not, you can just subtract the mean. So and the covariance matrix is basically like sigma xx, sigma xy, and so on, sigma y xc, sigma yx, sigma yy, sigma yz, sigma cx, sigma cy, sigma zz. So and basically each of these sigma xy, for example, is just what we have written earlier, right? X minus mu x, 1 minus mu y.
And the x is a time course or not?
Huh?
X, y, and z is time course or not? I mean the x, y, z is a factor or not?
Oh, it's scalar. Here I am showing scalar.
It's scalar?
Scalar, yeah.
So
scalar.
Not factor.
Not factor. So yes. Scalar, and I don't even need to assume to be zero mean. Like this can be a mean mu, mu is equal to.
I think if we scalar, so we don't have variance. What do you think?
Yes, we have this is variance.
Yeah, it is only scalar. I think this factor, x is factor, y.
No. It's this whole thing from new variable. Let me call it w. Let's say. Okay. W is like 3 dimension basically. Like you have 3 components here: x, y, and z. Yes. And this x, y, and z are scalar. And then the covariance matrix is basically this one, right?
Yeah.
So it's just this guy. But then if we look at our definition of this correlation coefficient, then I can also write this as like sigma xx, sigma x sigma y square root. Let's see, yeah, times rho xy. That's basically this one here. So sigma xy is equal to square root of sigma xx sigma yy times rho xy. So and similarly, this one is a sigma. This sigma, big sigma, can be written as this diagonal will be just sigma yy sigma cc, but the off diagonal I can like sigma xy can become like sigma xx sigma yy times rho xy in the square of that.
From above.
Yes, come from above. I just substitute like this rho xy here.
Okay, that's right. Yeah, and then this one also sigma xz.
Yes. So then, yeah, that's this like sigma xx sigma z and rho x and z. Yes, something like that. Now, if I consider this sigma here, and let's say if I have observed z, I want to look at the distribution of xy, right? And then from what we have earlier, so this should be equal to this guy here, right? So it should be equal to sigma xx minus what's that? Sigma xy, sigma yy inverse, sigma yx, right?
It has come from where? Is this come from where?
Oh, this coming from up here. Yeah, that's exactly what we are doing, right? If we observe a variables or observe some random variables, look at the remaining, because we already said it's a joint Gaussian, right? So we look at the remaining variables.
Yeah.
We will have a mean like this. The covariance matrix will be like this one, right?
So that's become covariance matrix.
Yeah, this is the covariance matrix of the remaining variable x. So in this case, the remaining variables is are x and y. Yeah, observing z, so we look at the remaining x and y. So, and sigma xx will be just this part. So this is sigma xx basically.
That is sigma xx.
Yes.
From where? Sigma, is this?
Oh, sorry, back sigma xx, this one.
Yeah.
Yeah.
Why that could be sigma xx? I think this is sigma xx.
Oh, yeah. This is a little bit confusing because we have big sigma and like small sigma. This is the big sigma is like as a matrix, right? So we use the earlier notation here, and the small sigma is like scalar. Yeah, that's I'm sorry. Like here it may be confusing, but here I'm copying the one equation up here, right? The equation up here, the big X here is actually x and y here.
Yeah, that's right.
Yeah, it's x and y here. So therefore, like x and y is like this portion here is sigma xx. So we want to look at like how this covariance matrix will be updated after observing like this part, like sigma observing C here. And now in this case, like this earlier, the Y here is actually Z. So so therefore like this actually is just sigma Z inverse.
Because in here we don't have Z component, so this is actually sigma XY, all of this. So because Z only here, yeah, that's right. So this one, there is no Z variable here. So this become XY, become this. That's right.
Oh. Okay, maybe I erase this part, like maybe less confusing. So from using the variables that we have earlier, it'll be something like xy, maybe I write a notation like that, minus sigma xy z, sigma z inverse sigma z xy, something like this. So like you may kind of like forget about this one here. So it's something like this. I'm just applying the equation we discussed earlier, right? So here like we want to look at like what's the covariance of like x and y after observing z here. So it should be updated like this, right?
Okay.
Yes.
Like that.
Yes. So and so therefore like this is basically just sigma cc here. It's like sigma cc inverse. And then like I have sigma xy is like this part, therefore like, and the sigma xyz is this part here.
Sigma XYZ, that part?
Yeah, this part is sigma xyz.
1, 2, 3, 4. And 1,
Oh, okay, just 1, 2 basically.
1, 2.
Yeah. Let me fill in the matrix again, like remaining of the matrix. This is like sigma y, sigma z, bo yz. Yeah.
YZ. That is what? That is this.
Yes, that's this part. Yeah.
So that's become there. XYZ. And then XY that. Because that XY. Because this is XY. So this comes in here, sigma. This one, XY. That's right. And this one, XYZ. Sigma XYZ where?
Sigma xyz is here. That one is the sigma xyz. So this part should be like sigma xx, sigma zz, bo xz. Actually, it's the same as this part, right? And this one is just this one, symmetric, right? Because the matrix is.
So why you call this a sigma XYZ? Why? Because why?
Oh, sigma cxy. This one is like.
Sigma ZXY.
Yes.
Oh, that's why. Why you call this sigma ZXY? Because this is Z.
XY, and this is XY.
This is XY. This is XY, and this is Z.
Yeah, this is like this 0 and the XY columns.
Oh,
Yeah.
okay, I see. So that's at the second position should be here and Z in here, and some is one. Also the first one XY, so XY should be that XY and Z in here. That's right.
Say that again.
For this one XY, so XY, so this is actually this.
Yes.
Yeah. XY
Yes.
and Z.
C column. Yes.
Z column.
Yes. XY row and C column.
Okay. Yeah, that's right. So the second one is should be column, and the second one should be.
Yes, the second one is the column. The first one is the row index. Yeah.
Okay.
But then you look at this, each of these have sigma cc here, right? Like if you multiply like this matrix here, so this is just a scalar, you can pull it out, multiply this matrix here is just basically is equal to how should I say, like this is a column vector and a row vector, a column vector multiplied by a row vector. So the 4 elements here will be just this one will be equal to this one multiplied by this one, right?
Yes, that's right.
And this one is equal to this one multiplied by this one, right?
Right.
Yes. So therefore, like the four elements there will be just sigma x6 square root multiplied by sigma zc square root rho xy multiplied by this one, so multiplied by itself. But you look at like for all these 4 elements here, there's sigma zc, right? Inverse sigma zc. Oh, sorry, square root of sigma zc. So then if you multiply like them out, like that's each term should have a sigma zc there, and that it will get cancelled like by this guy here. So then therefore like remaining what we have is basically sigma x, sigma x6. Actually just sigma x6.
Rho
Sigma x6 and rho xc square.
What square?
That's multiply these terms, right?
Oh, that is the same one?
Yes, it's same. And actually this is a sigma y rho should be xx square. Oh, wait a sec. Wait.
XZ.
Yeah, xc is correct. Xc is correct. Yeah. See, so yc, right? Yc square, right? And off diagonal is like rho xc, rho yc, right? Rho xc, rho yz, and sigma x sigma cc square root, something like this.
This come from where?
Come from this multiplied by this one, let's say. So it's equal to this multiplied by this.
Because this one is same. This one is same in here. So
Yeah, this
multiplied by
this one is same. This one is the same as this one. These two are the same.
And this is what you want to calculate. This one. This one.
Oh, well, we want to calculate the whole sum here.
But for that, you calculate only this one. Yeah.
No. This already multiplying the whole thing now.
No, I mean that for that only. I mean that for can you scroll down? This one multiply this one actually at z. It means that this one.
No. We have like this is a column vector, right? This is a row vector, right? When this is a 2 by 2, and we multiply. Okay, this is 2 by 1. This is 1 by 2. When we multiply these two together, it's like 2 by 2, right?
Yes, 2 by 2.
Yeah, and then each of the term is like just like this one is just this one multiplied by this one, right?
Yeah, that's right.
And then like for this term here, just this one multiplied by this one, right?
This one. Yeah.
And this is exactly right.
Yeah.
And this know that this two is actually transposed to each other. So this one is the same as this one here. So therefore, like this term is equal to this multiplied by this. Is equal to this multiplied by this, and will be like equal to like sigma xx, sigma yy, sigma cc. But sigma cc will got cancel away because we have this term here.
So where you put that? At where you put that?
Sigma cc?
Yeah.
No, I didn't.
Sigma xa square sigma xa times sigma yy.
Okay, yeah, I probably make a mistake here. Sigma x6. Wait a sec. Let me look carefully. Sigma x6 times sigma yy. Yes. Yes. Thank you. Okay, let me remove this. sigma x x sigma y y square root rho xc, right? Is that rho yc? Something like that. So this sum is the same, right? This two is the same. And then I have this one is just this portion of the matrix, right? So I have like this is a sigma x x sigma y y, and that one is what, like sigma x x sigma y y square root
From where?
o x y.
From where?
From here.
Oh yeah, this one.
From here.
Y y x y.
Yeah.
And then
This here is the same.
Same one.
This one is the same. Then now I have this subtract this, so therefore like I get like sigma xx 1 minus rho x z square, and this is sigma y y 1 minus rho y z square, and then the off diagonal is a sigma xx sigma y y rho xy minus rho xz rho yz. Yeah. So this one the same, so we don't care. But then now you look at that like uncorrelated. What does that mean? Uncorrelated just means the off diagonal.
Is this the same with this?
Yeah, this is the same. Yeah, it's symmetric, right?
Yeah.
So now if we say like it's uncorrelated, that means that like the off diagonal term, this one is equal to 0, right?
Uncorrelated.
Yeah, if like x and y are uncorrelated after observing z, then this term will be equal to 0, right?
Yeah.
So that's so we compute the proof. So basically like x y uncorrelated if given z, if like rho xy is equal to rho xc rho yc. And of course, for Gaussian, when it's uncorrelated, it also means independence, right?
It means that it
So
will be
it's
0 if xy or xy is equal to this one and this one.
Yeah.
So xz, yz, that's uncorrelated.
If this is satisfied,
Yeah, if that's
if this satisfied, then like x and y will be uncorrelated given z. And because for Gaussian random variable, when you're uncorrelated, it also means that it's independent. So it means that like when this happens, then x and y is independent given z. Yeah. So
that's why you say that this one uncorrelated.
Oh,
because 0.
This is 0. Yeah, this is
yeah,
0. Yeah.
Oh yeah, okay, that's right.
Yeah.
And uncorrelated in the Gaussian is independent.
Yeah. Yeah. We showed that earlier. So and actually from this proof you can also see like this way what happened to the off diagonal term. So after the observations, you basically your variance will shrink from 1 to 1 rho xc square. But of course, like this is actually just I mean you can just use this equation here. It's basically just essentially just this equation, right? But it's scalar basically. Then you get this result here.
That is scalar.
Yeah, yeah, because when it's both x and z are scalar, then your sigma xc is just equal to sigma xx sigma z. Oh, wait. Sigma wait a sec. Yeah. Yes, I think. Sigma xx sigma cc will xc, right? Something like that. Then you sigma cc is equal to just sigma cc, I think. This I need to have square root here. So then like
sigma cc square and sigma cc.
Yeah, and then
But when rho cc
Rho CC.
Yeah, rho CC.
Rho XC here.
No, I mean that for sigma CC, we have rho ZC.
You mean this?
I mean that in here.
Yeah, sigma CC.
In here, we have rho
This
CC.
is Rho CC.
In here, times rho ZC.
Oh, sorry, like my handwriting is sigma ZC here.
Sigma ZC and times rho ZC.
Oh no, that's no Rho CC there. Like that's only like sigma.
Because rho ZC is 1. That's right.
Yeah, Rho CC is 1. You can think of that way also.
Oh, yeah, okay.
Yeah. So then if you substitute into the earlier equation here, yeah, you can also verify, like if you substitute to here, you should just get back to this guy here. That's, of course, you also have like sigma xx is equal to small sigma xx.
If we substitute to there, and we get that, what do you mean? If we substitute to where?
Or substitute this to
This guy, this to that,
to this one.
that's one. Oh,
Yeah.
and we can find that.
Yeah. Then you should have this.
We have that.
But this is like a kind of like small kind of application to that. It's kind of nice because this you can see that this gives you a simple condition to see like when your variable will be conditional independence given some other variables when you are in Gaussian. So immediately I can kind of like motivate you like I mentioned last time about Gaussian process. So if you think of like Gaussian process in a 1D case, so it's basically just a one-dimensional. So I'm not a kind of rigorous way of explaining Gaussian process, but I just kind of a non-rigorous way to look at this thing. So like I have a Gaussian process you can think of like it's basically just a one-dimensional discrete signal here. So a discrete time. So I discretize the time axis here, and then like each of them is a Gaussian random variable, and they are jointly Gaussian. All of them are joint. So therefore, they have a huge covariance matrix, right? A big covariance matrix here. So and it's reasonable to assume that like you have conditional independence given some samples in the middle. For example, like if I have two samples here, it's reasonable to assume that like if I know this guy, I'll break the dependence between these two. Right? This is like just Markov. Yeah, it's just kind of this Markovian property, right? So it's like you only depends on like if you are given the samples earlier, then the samples like even earlier will not be important to predicting what we have here
But for
at the current time.
One, you said that if conditional independent x, y given z, it means that not Markovian. This is a Markovian, should be not 0.
It's Markovian. C
Markovian.
C is here. You have like y and x. You can think of that way, right?
X.
Yeah.
And it means that Markovian x x z is not 0. That's right. That's it. For Markovian.
No, when you say a Markov chain, it's just basically saying just.
It's something like this. X given y here given z is not 0. That is Markovian. That's right.
No. It's the opposite.
The opposite one.
Yeah.
Oh yeah. Sorry. So this one.
Yes.
Okay.
Because you form a Markov chain, right? Basically, like you greatly simplify the model here. It's basically assuming that okay, you look at every samples here. Think of it this way. So if I have one sample here, like xn, let's say, and I want to predict what is xn now, right? Then I look at the ideal, the crazy way is like I can look at the probability of xn given all the variable before that, like xn minus 1, xn minus 2, xn minus, and so on, like go to all the way to minus infinity. Markovian is just saying that, okay, given my last xn minus 1, all the rest will not give me more information, and therefore this is just equal to pxn given xn minus 1.
Yeah.
And this is actually just saying that like xn is conditional independence of xn minus 2 and so on, given xn minus 1.
Yeah. T minus 2. And it's minus 1. Minus 1. xn here, and it's 1 and 2 in here.
Yeah.
It's 1 in here. Oh yeah, that's right. So
And
something like that.
in particular, we can just say, okay, for the rest, I don't care, but just look at xn conditional independent given xn minus 2. I mean, like conditionally independent of like xn minus 2 given xn minus 1. And from our result earlier, we say that like this happen if we look at the covariance matrix. Like, it's kind of like hard to write. Maybe I just write this as x minus 2 and x minus 1, something like that, right? Then basically, maybe I even just use x, y, z here, right? What we have earlier. So xn minus 2 is y, xn minus 1 is z here. Then what we have is like we expect that like rho xc is equal to rho xy times rho yz.
Yes.
For that to be true.
That to be true, to make it true.
So then like, okay, now we further assume one more thing. It's like, let's say we assume the
So rho in there, something like what? In this data.
rho in there is the correlation coefficient between the adjacent sample. So you have like how this sample is correlated with this sample, basically.
Okay.
Yeah.
Okay.
So and now in particular, I can assume, let's say.
So what is rho xz in here? What is the data of rho xz in here?
Well, so let's say I call this is x, this is z, this is y, right?
Yes.
Well, xz is just a correlation coefficient between these two.
Oh.
So
it's only two data?
yeah,
Oh.
just like,
So it's
but
it's simple. I mean, that no need a lot of data. It's only two data in there.
wait a sec. We didn't assume that yet. But let's assume that it's stationary.
Oh, okay.
The signal is stationary, so the statistics doesn't change.
Okay.
So then that would be your what you just mentioned, right? Then I will just use one parameter to kind of specify the entire things here. It's basically saying, okay, like the adjacent variables, all of them have the same correlation coefficient.
Yeah.
And we may even assume that because like the covariance will be the sigma xx, it be sigma xx, sigma zz time rho xc, right? Something like that. Now we can further assume that like this is constant, right? So let's say this is like constant, doesn't change. It's just some sigma here, right? Then we basically just have one or maybe two variables to specify the whole. We can include the mean also. So we have three variables here: the mean of the signal. The mean may change, but we may have the statistics count, the second order statistic count fixed. So basically the covariance count fixed, and also like how it's correlated with the earlier variables. It's the same. And then in that case, you will have a covariance matrix will be simply like this form, right? So I have like the diagonal is all sigma. Let's all make it 1, just make it simple. So I assume like sigma is just equal to 1. So then the off diagonal will be like first off diagonal just rho here. So how about this one? What's this?
0.
No. What will be this one?
This one. If rho is 1, this is sigma.
This is like the same. This is the sigma matrix, the covariance matrix.
So let's say just this one. So this one. You ask this one and this one.
Oh, okay. This is symmetric. I won't ask you this one. This is trivial. But I ask you like this next one here.
What's that? This one. This one. And this one. This correlation in this one and this one.
Yes, yes. This one is the correlation between like the third one and the first one, right?
Yeah, this one.
And the third from the first one will be like this case, right? So I have like the correlation between like this guy and this guy, right?
Yeah.
And we know the correlation between this guy to this guy is equal to the product of correlation between this guy, and this guy with this guy.
Mm-hmm.
So therefore, this one will be just rho square, right?
Rho square.
Yes.
Okay, could you repeat?
Yes.
This guy, correlation this one and this one.
So now we have, let's say I have this term here. The correlation between itself is 1. With the next one, let's say with rho here. And then like, for this to be like the first term, I mean for this sample and this sample to be conditional independent given the middle one, we show that this one, right?
Yes, that's right.
So like, therefore the correlation coefficient between this and this has to be reported between like this one and this one and this one and this one. From this guy, right? Just from this guy here.
So where is the rho xz in here?
So for example, like this is x, this z, this is y, right?
Oh yeah, that's right.
Actually, I here I have like x, y, z here.
X, Y, Z.
If I write it this way.
Okay, so
yeah.
This is rho z x in here. It means that rho x y times x z. So
no, rho x y times rho y z.
Oh, rho x y y z, and this is rho and this is rho.
This rho, yeah.
So rho times
So that's just rho square here.
Okay, that's right.
Yeah, I can like do the same thing, right? If I ask like what is the one next to this one, then we'll be like again like because I have the conditionally independent property. So then the correlation coefficient between these two guys here will be equal to the correlation coefficient between these two and these two. So it'll be rho cube then, right? Because this is rho square, this is rho, then I rho cube here. So therefore, you just specify one correlation coefficient, and maybe also the covariance, the variance of each of the sample. Then basically you have the entire covariance matrix is defined. And this is basically the Gaussian process. So you have like very few variables here actually, but it is kind of interesting. Like you start with.
But there is how about if random walk? I mean that how if the station not station, if unpredictable. How is unpredictable? It is so I mean that it's deterministic.
No, it's not deterministic.
Not deterministic?
No, it's not deterministic. You only specify the covariance matrix and the mean, right?
Yeah.
And then you draw some sample there, like it can be. You just give a distribution. Distribution is deterministic.
Okay.
But like every random variables have a distribution. Distribution is the deterministic, right? But what we are saying is like if you observe something, it will change the distribution. But whatever sample you draw from that is still random, right?
Yeah, still random. But we have a distribution on there.
And the distribution will change, and you know exactly how it changes. It's kind of nice. For example, like you can start with assumption like this, right? You can start with assumption that the covariance matrix is like this one, and maybe zero mean. Actually, I can. Maybe it's better I show you some example. Like, let's see. don't know where
But
is
the statistic is still same with the random. That is still random.
It's random. Like this one is showing you. I have like 200 samples here, and then basically the original distribution is zero means. I assume the whole thing is zero mean, right? Whole thing is zero mean.
Zero mean? That is.
No, okay. I'm sorry. Like to start with, is zero mean. So like this already is showing like I draw one sample here.
Oh, okay.
So.
Basically, that is zero mean. Firstly, that is the PDF and Gaussian.
Yes, that's a P. Wait. You need, no. This is not a. You need to read it this way.
Okay.
This is a John Gaussian. Like you have 200 samples here.
Okay.
Each sample here have like a distribution, right?
Yeah.
It's like unknown. Now, for example, I have this point here, the particular point here, maybe it's like 25. For 25 here, the mean is 0, so this is showing the mean, and this is showing the variance. So if 25, like say with mean 0 and the variance is like 1, let's say. I forgot, like I'm showing the variance or standard deviation. I forgot either variance or standard deviation. But then, like after I draw one sample, then the whole distribution change, right? So basically, it's showing okay. I draw one sample here. I observe a sample here is like 130 maybe somewhere, and then like it's equal to 1.5 or 1.6.
That is the mean.
No, that's the observation.
Observation.
You made an observation there, right? Remember our model here. There's correlation between the current sample with the adjacent samples, right? The whole line is correlated, right? So therefore, like when I observe something like this, I pull up the entire mean of all the labeling samples, right? For the adjacent random variables, now they have a mean kind of like farther away from 0 now. It's much closer to this like 1.6. And actually for the one adjacent to it, it'll be like pretty much close to that mean, right? Close to the observation. Now, of course, at the observation point, that's exact, right? Now it's no longer deterministic because we already observed that, we confirmed that, okay, that is the point, the exact value is equal to that. So now, therefore, you see the variance now is 0.
The variance 0.
Yeah. Okay, this again, this is showing the variance. The width here is from the mean, and this,
So what is
I
the
think
mean?
it's 1 sigma or something.
This one the mean. This one mean.
The
The blue one is
The blue
mean.
curve is the mean.
Yeah, the blue one is mean,
Yeah.
and then okay, this is the mean, and because and this is the variance.
Yeah,
And
it's-
because the variance is same with the mean, it means that the variance is 0.
Yeah, the mean is 0. The variance is 0. The white curve, okay, the white curve here is like, I'm showing like mean plus sigma. Basically, it's mu per sigma, mu and minus sigma, right? The upper one is mu per sigma. The lower boundary is a mean minus sigma.
Mean minus sigma.
Yeah,
Yeah, yes. And then
yeah. And then you see like, I after making one observation, I have changed, right? So according to what I observe here, that will affect the distribution of all the other samples.
it means that we can predict another sample in here
Yeah.
by using this one.
Now we have prediction like based on the prior here is we assume is 0 means, right?
Yeah.
But because of this one observation, like we adjust our bias now, like adjust like how we believe like those samples mean supposed to be, and also the variance is also like adjusted, and I can have more observation. Let's see, I should how does it be? Oh, this is this already like it's already 7 observations. Let me start again maybe. Like I have 2 observations here, like 1, 2, right? Then like between these 2 now, I become more kind of confirm like what those means supposed to be, right? Now you see this difference between these 2 upper and lower white line now it's getting much closer, right? So
your observation is this one and this one. Our observation is this one and this one. It means that we know this, the red one. We know this.
again, like the upper white line and the lower white line is the mean plus variance and mean minus variance.
Yeah, mean plus minus mean plus variance.
Yeah.
And we know that. That is our observation.
We know that because we're using the formula, right?
Yeah.
We use the formula. Basically, what we did here is we have two observations, right? Now, so if we go back to here, basically, go back from the beginning here, it's like this is your observed y here, right? Now it's like you have two observation y, two y's here. Then you modify your mean and now the variance, right? The only thing additional is like we change like what is the initial like sigma and the mean here. Our mean here is simply zero mean, and the variance here is I have the form as I mentioned. It's a form like this, because we want to have conditional independence. We want to have Markov property for the line there, and
we can find that. We mean that we know this. Yeah, we know the mean then.
We know the mean. Yeah, we know the mean. We know the mean. We always know the mean. But like what I mean is like, for example, like if we ignore the, for example, for this point here, we have the pi is like the mean is 0, right?
Yeah.
Because that's basically the pi. We always have the mean there, but that's our pi belief. But after some observation, we'll adjust this pi, right? So for example, like for this one here, for example, in this range here, we become much more certain. The mean is not 0, right? So this one is probably like this is where the mean is supposed to lie.
So it means that the mean is not always 0. Sometimes it will be going down and then it's going up.
No, actually, no. I'm not sure you still get what I'm talking about here. So I have many means here because I have 200 samples here.
Yeah,
right?
That's right.
So like each sample can have different means.
Yeah.
Yes.
Sample can different means.
Yes.
Okay. In here, for example, here, this is different. Not this is the same and this is different.
Yes.
Okay.
Yes. Initially, we just assume everything has the same 0 means here.
Yes.
But after make some observation, we can adjust that.
You can adjust that.
Yeah, using that formula. Yeah.
So what is the this is our sample, and what is the goal of that? I mean that.
This is like some kind of prediction, right? You can think of, like for example, you have you have like a one-dimensional signal here.
Yeah. Yes.
And for example, like even the simplest usage can be like interpolation, right? For example, like you have a 1D signal here, and I do some reading like kind of like irregularly, right? And this is another method of doing interpolation, right? I just sample like at 5 seconds I sample one, and then like maybe like 7 seconds I sample another sample, and then like 10 seconds I make another samples and so on.
Yes.
Then I can do a kind of interpolation. Like it's like you can do a polynomial interpolation. But interpolation like this have like some advantages because first, it will be more stable, like robust than like you use polynomial representation, because polynomial, you're not sure what's the degree you're supposed to, because if you have the degree is too small, then you will have like strong bias, right? If your degree is too large, you have strong variance.
Yeah.
So, and you're not sure, like you start from the beginning, what is the degree you're supposed to set. And another advantage here is like you actually give you more information than just the curve, right? Because if you do interpolation, you do not know like which point is accurate, which point is not accurate, right? This also gives you some information like which point is more, like for example, I give a prediction here, the variance here is bigger, so it's quite a bit bigger than for example variance here. Yeah. So like these points here, the prediction most likely is not very kind of reliable.
Yeah, that's right.
So this gives you some kind of like certainty, like give you some belief, like what is useful, what is not useful.
Okay, so it means that our belief in here is really increased.
Yeah.
100% maybe. And here is not.
You can say exactly here, right? Because the variance is so much. Right?
Is so
very precisely, like
precise.
How.
But we should know the variance. We should know the means also in there. That is our observation, mean and the variance. and this is one. This
No,
one
you
is,
you mean at the beginning or?
yeah, at the beginning.
No, at the beginning we didn't have. So remember, like what we have at the beginning, we don't have anything at the beginning. Honestly, at the beginning we only specify this covariance matrix, right?
Yeah.
So the only parameters I input in is row here,
Okay.
right? And then I assume zero mean I put a row here and that's it.
Okay.
Yeah, I didn't. Of course, you can adjust that if you think like the variables are more correlated. When you change the row, like a higher row will just have the samples to be more correlated, right? So will affect the labeling pixel more strongly.
So how about this is a 200, and
Yeah.
how about in here? How to predict 201?
But it's the same thing, right? It's like you can,
Just
yeah, the same thing. I stop here, like you can have to.
just make some example again. One here, one here.
I mean, like I have 200 here. It's just like my sigma. Then I just use 200 variables here. Then that means that my sigma here will be like just 200 by 200, right?
Oh.
So you can increase it arbitrarily.
Oh.
Yeah. But of course, it increase the complexity. But yeah, you can. Yeah.
And now that become deterministic. I mean that we can find the.
You can say the prediction is deterministic,
Yeah.
but it's not deterministic, right? Because
For example, in here, because we don't have variance, so we can find.
oh, okay. But that point, of course, because that's the point you made the observation, right? That's the assumption here. Right? You made the observation. The observation is exact. Okay. Actually, we will talk more afterward. Like, how about if you have observation is not exact? For example, like your observation is noisy, then it won't be like using the conditional. Then you need to multiply some Gaussian.
Yeah.
Just will immediately talk about that. But this is a nice demonstration.
Yeah.
Yeah, just
It's nice. I mean that.
for example, like now is I have one more observation. You see how it's going to change, right? And I can have more. So now when I have like couple here, this become very much exact. So it's here I'm very certain like what this variable is supposed to be.
Yeah.
And this after 7 samples here.
But the prediction is something like beyond of us in time.
Oh, it's okay. You just extend it. For example, I predict in the future, right? You can think of like I only observing like this in the past, right?
Yeah. That is
So you can assume that okay, here is exactly what happened, right? You can think of like my present is 170 here,
Yeah.
right?
Yeah.
And then like these variables are all the past. Then it will predict the future, right?
By what?
Well, this is exactly what's going on. Right? If you only samples like in the past, then you will have like.
But we don't know this one. Before this, we don't know this.
Yeah, you don't know this, but you still make prediction here, right? You see.
Make oscillation.
No. We already have prediction here, right? Here we have like 7 observations here. I think like some points here, but the last couple is like here, right? So we don't have any observation here, but you see we still have prediction here, right?
Oh, I see. So it means that this is actually our data until here, but this is just prediction.
Yeah.
Oh, because we have a sigma is a 7 to 7. I mean that what this mean?
This is 200 by 200. Yeah.
By 200. Therefore, you can find another this. Yeah. Yeah.
Basically, yeah.
And you find that a row in there, and can find all of these 200 by 200. Yeah, because the row in a sigma in there is 200 by 200, and then you can find this one. Or even our data is only from here.
Yes.
Oh, then that's how it's something like.
But of course, like this is Markovian, so therefore, like if you have data observation, like observe here and so on, then maybe like more data in the past, it doesn't help too much here. But
we can.
well, I'm not 100% sure. Maybe it's still like I don't know. maybe not actually. This is kind of interesting because if you think of like I only make observation like this one here. From the information, I don't know how it is able to predict it's going up again, right? Somehow like it's the other observation actually help to make this kind of like prediction.
That is because that is come from rho we have. That is come from sigma. So if we already know the before and this one data, so we can find this one too. So this is also come from the past data, the past data.
Yes, but I'm thinking like it's the Markovian property suppose suggests that like given the previous observations, then all the other observation is kind of not useful, right?
Yeah.
But here, honestly, I don't know how to explain that. Like I actually I won't predict that like it's able to predict like this, because like based on the previous observations, it will just say that it's in this range, right? And for this guy, is able to say okay, afterwards it should go up somehow.
Yeah.
Then it means that the other observation actually make kind of create this adjustment to this prediction here.
Yeah. We can find a future by know all of this data, something like this, because this is the sinus, something like sinus waveform. So actually, this is come from past. We can predict the future from the past.
Yeah.
If we know this like this, because in here, if this our data, this is now and this is future, so easily. But this is still random. Yeah.
Yeah.
This is still random.
Yeah, it's random. Yes.
Yeah, because we still have the variability in here.
Yeah.
So, but we have range with this. We can find this is okay or not to open something like trading or not. But in here that will be joined again with this one, with this form. It will be joined again, and this is become more not random. So we can predict the future.
Yeah, you can predict future, but not predict very far away. Of course, you are able to predict future. Yes.
Maybe we can try that to real data.
Yeah, you can play with real data like
Yeah.
let's see.
Just financial put on there and find the means and then sigma
Yeah.
and find that is correct or not if we using financial data. But that should be in Markovian chain.
I mean, like as I mentioned, like the Markovian like property is already embedded in your initial coherence matrix, right? Oh, but okay. I see now why it happened like this, because the original assumption is I assume this is conditionally independent, but maybe after the observation is no longer conditionally independent.
Yeah, that's right.
So therefore, like
not Markovian again. If not independent.
So, but anyway, this is kind of course, you can extend it to higher dimension as well. So if you do it, for example, 2D, then, but of course, like complexity will kill you, because like if you look at this guy here, like you need to solve kind of inverse the coherence matrix, right? Kind of stuff like that. So but actually this part is fine. If you make this is your observation here. The observation, if you only have a few samples, and that the matrix size here will not be too big. Yeah.
It was ZZ. That's that.
Yeah, you need.
If ZZ in here is that's only one dimension.
So if you only observe one samples,
Yeah.
but then like yeah, you can do that also. Like you can sequentially. I guess the code I didn't implement like this. Each time I just use the whole. Yeah, but of course you can like easily modify your code to do that.
That is code in MATLAB.
Yeah, I just wrote in MATLAB. Yeah,
Can
so it's
you
very simple.
share to
Yeah, sure.
us?
Yeah.
Yeah, so we can try another one. And like play with that code.
Let's see. Actually, I'm thinking to make it as a homework. Let's see about that. Like,
Now with that, I want to play with that.
yes, but it's very simple. Like, I guess it's better to assign as homework because this is only just like this. Like, you can write it just very simple. Like, I mean, the code it doesn't really has much.
Yeah, that's
So
right.
yeah. So yeah, I guess it's a good time to stop. I guess we'll just take a break for 15 minutes, then come back.